Hi, I'm Madeline James, and welcome to the 9th part of my world building and Earth-like fantasy world building guide. If you saw the last videos, in the last part we worked on weather events, but before that we were working on mapping all of our climate regions. And we can't get too much more detailed than that on a global scale, but we are going to do what we can to figure out our rivers and our wetland biomes. If this is the first place you're jumping in, I will link the start of the guide down below because we are going to build on a lot of the maps that we've created in earlier parts, but let's get started with rivers. All right, so for some reason, rivers tend to have some of the greatest, most egregious mistakes in fantasy maps, and you know, this might be because there's enough people that understand how rivers work enough to kind of point out these mistakes, which isn't necessarily the case with a lot of other geographic features. But it's definitely a place that people look for advice very frequently. And once you kind of have an idea of what the rules are of rivers, it'll be very easy for you to recognize these mistakes as well. And a significant part of river mapping and world building will only be relevant on regional and local maps. So since we're only working on the global scale, we're kind of going to discuss the laws of rivers, which apply at any scale, as well as large watersheds, major rivers, and wetland regions. When we get to regional and local maps, we can expand on this to include smaller scale features and more minor rivers and wetland regions as well. So, laws of rivers. The most important thing to remember with rivers and any wetland feature is that they are made of water. Surprise! And it may seem obvious, but you would be surprised by how many people forget this. Water will always follow the pull of gravity along the path of least resistance. When it's raining, water droplets will travel down the window. In the shower, water will fall down to the ground and then make its way to the drain. And so a few major laws of rivers. So first, rivers will always, with no exception, flow downhill in the path of least resistance. 2, rivers will eventually carve a path through almost anything, quicker through softer materials, slower through harder materials. 3, rivers join, but they never split, other than at deltas, but that's not really them splitting. We'll kind of talk more about that later. And there are a few really small sort of exceptions to this, but they're extremely rare and very small scale, so just don't think about them at all. 4, rivers almost always end up in the ocean. It is the lowest point that gravity can take them, and there's maybe 10 to 20% of rivers that end in other ways, such as evaporating fully in a desert, going underground, and meeting inland seas, lakes, and wetlands. The reverse of these laws account for some of the most common mistakes in river world building. Rivers that split, rivers that flow uphill, rivers that connect different oceans, etc. So, parts of a river. Not only do rivers have to start somewhere, but they are also not the same at every point along the river. So let's break down where you will find these different parts and what the different characteristics of them are, because this will help in putting them on a map. So the 3 main parts of a river, and there are a lot of different names for all of these parts, so you may have heard them differently, but we have the headwater zone, the transfer zone, and the depositional zone. The headwaters are where rivers originate. To be obvious, the source of a river is water. Think rain, monsoon, snowmelt, and glacial melt. And since rivers flow downhill, they start uphill, aka in mountains. The complicated part is that the water starting these rivers is not going to be consistent across your map, and it will differ seasonally. In rainy, wet seasons, there will be more water to flow into rivers and less in dry seasons. You can even have seasons where the rivers will completely dry up. Snowmelt is going to increase with the temperatures, so snowy, wet mountains that have very hot summers will produce a lot of snowmelt. I think you get the idea. So these headwaters, which are also called the upper basin or upper course, will be in the steepest initial parts of the river. So here the water will flow very quickly and it's going to cut deep V-shaped valleys, and you will frequently find waterfalls and rapids as they quickly descend in elevation. The rivers here can carry a large amount of sediment or a large bed load because of how quickly they are moving. You can see on this map here, one up in the mountains is the headwaters. So next, number 2, is the transfer zone, also called the mid-basin or middle course of a river. And this is where a river has left the steep terrain and meets gently sloping hills. The water will slow down a bit, and rivers will start to meander. The river channels will widen here, and you will find floodplains in flatter valleys. Floodplains, if you don't know, are areas where water will overflow the main river channel and flood the surrounding low-lying land, depositing sediment that has been carried by the river, and these make the area very fertile. The predictability and severity of these floods have a large impact on the civilizations that try to settle here, which we will get to in another part of the world building guide, but it's very cool. So then 3 on this map is the depositional zone, also called the lower basin or lower course of a river. And this is where the rivers have left the gently sloping hills and now flow through broad plains and flatter valleys. The rivers are moving the slowest here and they reach their widest points. They now meander significantly and have very large floodplains. They will reach their terminus at the end of this zone, usually the ocean or an Endorheic Lake. More on that later. And here you will commonly find a river delta. The more a river slows down, the less sediment it will be able to hold. At a river's mouth or the end of the depositional zone, you will frequently find some of the slowest moving waters in a river. This means that a large amount of the sediment will be dropped, creating a type of wetland called a delta. And we will go into different kinds of wetlands later. Alright, so let's talk about drainage basins and watersheds. So, a drainage basin is the area of land in which all water flows to a common outlet. So there are 3 main types of drainage systems. There are exorheic, endorheic, and archaic. And I've seen different pronunciations for these. I don't really know if it's exorheic, exorheic. We'll go with heic. I don't know. So exorheic systems are going to drain to the ocean, and they're the most common, covering about 75% of land masses on Earth, excluding the glacier-covered areas like Antarctica and Greenland. Endorheic systems are closed systems that end inland, either by evaporating or seeping away, and this is normally in very salinized lakes that can be temporary or permanent, and we will typically find these in arid regions. And then the last one, archaic systems, are mainly temporary and are much less predictable. They're commonly found in more arid regions as well, and these systems are much smaller than the other 2, and we won't be considering them on our global maps because they just kind of pop up randomly in places. Well, not randomly, but you get the idea. So, the global ocean drainage map that you can see here shows the major ocean drainage basins on Earth. All regions other than the gray areas are exorheic basins that drain to an ocean, and you will notice that the inland divides between these basins are mostly mountain ranges or the most highest elevation points kind of connecting them. A drainage divide is these ridges or hills that separate the 2 drainage basins or more. And on each side of this high point of these drainage divides is where water is going to flow in different directions. So for major basins, these will all empty into Endorheic lakes or into an ocean. And these major drainage basins contain a number of smaller ones typically. You can't see them on this map, but typically smaller river systems that flow into the same outlet but don't connect with the major river, or the drainage basins that lead to smaller rivers that empty into the major river of the drainage system. We are going to start our global river map by dividing all of our landforms into major drainage basins by marking the drainage divides. At this point, it doesn't matter how much water or precipitation can be found in these areas on each landmass, ignoring areas covered in glaciers. Draw lines along the highest points of your mountain ridges are hills. And you can also ignore small islands where the scale is too small to worry about on a global map. So the exact size to include is up to you, but I tend to ignore anything smaller than like 5 to 5 degrees, 5 by 5 degrees as you would measure around the equator. And the low granularity of our global elevation map is going to mostly lead to us only finding the major drainage basins anyway, but if for some reason you went a lot more detailed and you get a lot of small basins together that flow into roughly the same base, you can kind of combine them. So you can see here that I went through and I marked along all of these major mountain ranges, and then I sort of connected the different basins based on the highest elevation points along them, and then connected them out to the oceans, essentially. And because we don't have that much granularity here, you are going to have to make some decisions, right? Like in my map, you can see that I have this line falling down basically across the same color. So if you look right around here, this is all the same color of elevation. This is all the same color of elevation, but because you can see this kind of swoop here, this sort of means that if you were to draw a line this way, this point is where it's going to be the highest in elevation. So I'm sort of imagining that that extends further up this way. And these assumptions that we're making, you're kind of going to have to just remember them as we go. And when you're making more granular maps, you'll just kind of have to keep this in mind, right? That these are going to be your highest points, and maybe we'll use that when we get to our elevation maps. But just, you are going to have to make some decisions here about that. Or if you really want to go through and make a super detailed elevation map, you can, but I don't think it's really necessary at this point. All right, so now you will find a decent number of inland basins that do not connect to the sea. Not all of these will be endorheic. Water has to go somewhere. Either it will evaporate at a significant enough speed to be contained within this region, creating an endorheic basin, or it will eventually cut a path to another basin or ocean. So consider each of these inland basins one by one. Look at the aridity level in each season. If the lower lying regions of this region are very arid year-round, and there's no easy path for water to cut to an ocean, mark this as an endorheic basin, with the lowest point being an endorheic lake. And try to keep this to 20% or less of your total glacial land area. Otherwise, consider the elevation and terrain, and we will try to determine how the water will escape. And this can be easier to do with much more granular elevation, like you would find in a regional or local map, but we'll do what we can. So you can see in the maps I have here, I had 2 inland basins that were sort of created, and based off my aridity maps, I determined that the one in the northern hemisphere would be endorheic, and the one in the southern hemisphere would not be, because it's just too humid in that summer solstice in the southern hemisphere down there. And there's a lot of spots on this map where I probably could have divided up more basins just based off guessing how I think the elevation would really play out. But I decided to kind of keep it a little bit more higher level and a little bit more general, just to make this a little bit easier. All right, so for endorheic basins or inland basins that you've determined should actually be exorheic and should drain out, what we're going to want to do is actually map the path the river water would use to leave this basin to figure out which other basin it connects to. And remember, water wants to flow downhill, and it will take the easiest path necessary. So once you reach the most downhill point, where you can see here I sort of have this little lake gathered where water's going to pool there, look for the lowest elevation around it. That will be the point it will cut through. Maybe find a valley and slowly cut a river through that. It'll also depend on how hard the material is. Water will cut through softer rock faster than harder rock, but we can't really tell that right now. But continue this process until you reach another basin or the ocean. We are not looking for exactness here. We're more just looking for a general area so that you know which basin to connect it to. So you can sort of see in this map I have here, there's pretty wide chunks of this higher elevation color here and even further up here, whereas over here it gets pretty thin, which sort of to me indicates that there's more likely for it to escape out over here, and also it's a lot closer to lower elevation over here, so it would make a lot more sense for it to sort of cut a path through right here. And this is just kind of something that you have to kind of feel a little bit by intuition slash, a little bit of pattern matching slash just make a decision and honor it later. At this point, I have split up my basins a little bit further just when I was looking at how the rivers would flow. And then I've added a section for basins that are a little bit too divided to really map out on a global map like this. So you can see all the light gray ones, mostly on coasts where I have mountain ranges right along the coast. They're too divided. The water's not really going to pull into any sort of major river here, so I kind of just marked them like that. And then you have my one endorheic basin there in the middle of that northern central continent. All right, so let's talk about major river systems. Within each of these basins, there are going to be major river systems consisting of a major river and its tributaries. And each tributary will have its own smaller basin within the major basin, if you remember from above, but we won't map that right now. If you look at the yellow basin on this global map here, located in central North America, you will find the Mississippi River Basin, which is dominated by the Mississippi River, and which terminates in the Gulf of Mexico, which, if you're not familiar, that is right here. Now we're looking at the Mississippi River Basin map a little bit closer up, and you can see that this major river is divided into the upper Mississippi and the lower Mississippi, ending in a delta in Louisiana, which, by the way, this delta covers 3 million acres and creates a 1.4 million acre swamp, which is really cool. But you can see that this map shows you these smaller basins belonging to each of the major tributary rivers that feed into this Mississippi River. So you can see the Ohio one, the Tennessee, Arkansas, Red, White, and the Missouri leading into this. Mapping our major river systems. So the first step is for each of your basins, you are going to mark the headwaters. And these is sort of going to be the areas that will include a lot of smaller rivers that aren't really notable at a global scale, just sort of where all that water is starting to gather up. And in each basin, color these areas that are steep, lower in elevation quickly, and are mountainous, where there are no clearly defined valleys for rivers to already be joining together. So you can see here in this map, I chose the highest elevation kind of colors here and kind of just hugged these higher elevation regions along here and down here. And these are going to be the headwaters of this basin. So now look along these headwater areas and compare them with your precipitation and climate region maps. You're going to want to identify the spots that would result in the most water flowing into that same valley, and look for regions with the highest precipitation year-round and areas potentially with the most snowmelt. For there to be much snowmelt, temperatures in summer must be mild or hotter to melt the snow, and winters must be cold or colder with precipitation in order to build the snow. So the colder winter is and the more precipitation, the more snow there will be to melt. The warmer summer gets in comparison, the more snow will melt, etc. And you can see here on my map, I've sort of circled 2 separate areas that are going to be the highest in precipitation for different seasons. So in winter, you're going to see that northern area, those rivers will flood in winter. They'll be the most full, or flow the most. I'm not sure what the right terminology is there, but they will be the most water flowing into the rivers there. And it's too hot in this region for much snow, so we don't have to consider any snow melt, just precipitation. And then in the south, we're really only seeing precipitation there in summer. So the rivers in the south will flow heavily in summer, and so you'll sort of see this alternating effect in the rivers in this basin. Where to start following each river, right? Where's the most uphill part of the major river in these different drainage basins going to be? So each major basin will have a major river, but the density of significant tributaries will be based on the amount of water that is feeding into that system and the geography. So tropical and temperate climate areas will have the highest density of tributaries, while polar and arid climate areas will have the lowest density of tributaries. And the exact number will be based on how you divided things up, like how divided the landscape is by hills and smaller rivers, by hills and smaller ridges. And you can decide how major of a tributary you want to map globally. If you want to only mark major rivers, that's fine. If you want to get as detailed as you can reasonably distinguish, that's fine too. My rough recommendation for the density of rivers, there will always be at least one, your major river, is for tropical or temperate transfer areas to have one river per 5 by 5 degrees of area. And again, measure that sort of based off right in the center of the equatorial area. And then for continental transfer areas, one river per 10 by 10 degrees of area. And for arid or polar transfer areas, one river per 20 by 20 degrees of area. And remember that this won't be an exact number. Allow for a bit of gut feeling based on the amount of precipitation and humidity and how divided the geography is. If it just makes sense that there would be another river over here, then draw it, because there would be. So you can see here on my map in this drainage basin, it's pretty arid year-round. So I went with 1 to 2 rivers, and because I do have those 2 different central headwater spots, I know I'm going to have 2 major rivers. So that's what I went with for this one. But let's look at a wetter basin. So here you can see in summer in particular, it's very humid and we see a lot of precipitation. So for a similar area, I'm going to have 6 to 9 rivers instead, which is a big difference. So let's track these rivers to an outlet. So we're going to follow each of these rivers downhill until they reach an outlet. Till, if these are exorheic ones, it'll be the ocean. For exorheic basins, you will have 1 river crossing most of the basin leading to the ocean. And you may have shorter rivers leading to the ocean as well. This is technically a separate basin from the one you're mapping, but we're not trying to get that granular, so it kind of all goes together. For the most part, your extra rivers will be tributaries that feed into your main river. And the endorheic basins, if there is a large lower lying area for your water to pull into, you will likely have a large endorheic lake, which you would actually see on a global map like this. There will likely be some smaller ones as well, but they probably won't be visible on your map. But otherwise your rivers may all evaporate away, slowly disappearing into what is likely a large desert. So you can see here in the top left, I have my more humid, wetter drainage basin, and so you can see I sort of drew in those maps sort of based off how I sort of imagine it would go. And again, I don't have super granular elevation maps, so I can't map them out exactly, but you get the general idea. And then on the right, you can see I have my 2 rivers that sort of meet together there near the end for my more arid drainage basin. Something to keep in mind is that even the widest of your rivers are going to be a lot less detailed at this scale. There will be far more meanders if you were to look at a regional local map. You're sort of mapping the rough location of the rivers at each point. So if you look at the Amazon, which is considered the widest river, during the rainy season, the widest points can reach 30 miles wide. And while that is astonishing for a river, it would be difficult to see this on a global map without zooming in a lot. So additionally, without a full gradient topographic map, we can't know exactly the path these rivers would be, so you do need to take a little bit of artistic license. Rivers will have to move around hills and bridges, and in flat plains they will meander. And play with them until they look reasonable and the way you want. And they can always be changed later if need be. This is just a little look at my map, trying to get these rivers figured out. I left in the red where I have my headwaters, and the little slashes I made were for snow accumulation and snow melt. So if I thought snow could accumulate there, I marked them with ticks in one direction, and then if I thought there was enough heat in summer to melt some of that snow, I added ticks in the other direction, just to kind of remind me visually when I was looking at this. And then I made little notes along the sides for each season of how arid it is and how much precipitation they're receiving in those regions. And then based off this map, I just went through and drew in all of my rivers, looking at it overlaid on my elevation map. Just to give you an idea of how I kind of went through and did that. But you can definitely see which areas on this map here are going to be a lot more arid than others. And so these are all of those rivers shown over my drainage basins. Alright, so Endorheic Lakes. As we mentioned before, endorheic systems will typically drain into an endorheic lake. And these tend to be among the largest lakes in the world. So due to the amount of evaporation that happens in these regions, these lakes are also pretty salinized, just like the ocean. And the largest endorheic lake is the Caspian Sea, which is also the largest lake in the world. And the Caspian Sea is approximately 143,000 square miles, or 371,000 square kilometers. And that's about the size of Montana or the entire country of Germany, which is crazy. There are around 130 different rivers that drain into the Caspian Sea. So that should give you a little bit of an idea for what we're mapping here for these. And these endorheic lakes will be the lowest elevation points within the endorheic system. And remember, if they have a way to drain to the ocean, they will, but then they wouldn't be endorheic lakes and systems. Let's move on to wetlands. But we've already covered delta wetlands and endorheic lakes, so now we need to talk about some of the other wetland features. And to remind you of what creates endorheic basins, it's where you have a faster water output through evaporation mainly than water input. But what happens when the reverse is true? if you have water entering the system faster than it can leave, it is going to pool. This creates wetlands. And wetlands tend to be in flat areas with large amounts of rain. And there are many different types of wetlands, but what even is the difference between a bog, a fern, a marsh, a swamp? I assume you already know what a lake is, so we won't throw that one in there too, but it is technically a wetland. And you can sort of consider them on a scale of nutrient levels, affecting the type of vegetation that can grow there. And for the most part, we won't get into the fine distinctions and types right now, and we'll just kind of be marking some of the general wetland categories based off where we would find them. So first, bogs and lakes. Bogs are a type of freshwater wetland that has poor soil and a high peat content due to the acidic nature of the groundwater and the many years of decaying plant life. And you will tend to find bogs in polar and colder subpolar regions where permafrost, which is a subsurface layer of soil that is frozen year-round, basically prevents too much water from flowing into the ground. And they are basically depressions in the ground, sometimes filled with rainwater and not a constant source of water like a year-round stream. Most bogs are pretty small and not anywhere near big enough to show up on a global map, but that isn't always the case. On Earth, the largest bog, or series of bogs, is in the western Siberian lowland, and it covers more than 1 million square miles. The lakes we are mapping right now will be freshwater. They can have many source rivers, but they will only have one river leading out of them. And if they don't have a river leading out of them, they're considered a closed lake and will not be freshwater. So, let's map some bogs. The sources of the largest bogs and lakes are depressions from past glaciers. The Great Lakes in North America were created by glaciers, for example. And look at the reaches of your last glacial maximum and identify a few areas that would have lake basins created by glaciers that have since melted. When we did our physiographic regions, I think we added some of these already, so you may already have some lakes in the areas where these would have been created, but if you didn't do that, go ahead and add some of those now. And specifically look for areas that would continue to have poor drainage. Based off the topographic maps, I guess. These areas must also be wet or wetter on our precipitation map. So add a few major bogs in continental subarctic climate regions. So this is going to be DFC, DWC, or DSC in lowlands where water would be trapped. And put some large deep lakes where these glaciers might have depressed the land significantly, between mountain ranges most likely, in or near the headwaters of a river you have already mapped. So you can sort of see here in this sort of pink color here, I marked all of these DFC, DWC, DSC areas with a circle, or well, a shape. I circled around them. And then I went through and looked at where I thought it would make sense for there to be enough precipitation and enough pooling in order to get some bogs, which I then drew a few in. Mostly you can see one up here, here, a little bit here, up here, and then over here and over here. And that's sort of where I drew my bogs in. You won't have that many of them. Alright, so marshes and swamps. Marshes and swamps can be fresh or saltwater and are essentially very shallow lakes. They are more common in tropical areas due to the need for a lot of precipitation and the sediment in the water. Marshes are dominated by grasses and shrubs, while swamps are dominated by trees. So in freshwater marshes and swamps, you will generally find them inland, while saltwater marshes and swamps are found in coastal regions where the waters can mix with ocean waters. And deltas and low-lying regions where water floods during high tide are some of the most common areas for saltwater marshes and swamps. So freshwater marshes and swamps can occur at parts of rivers that are very slow-moving, along the edges of lakes, or in depressions in the ground not quite deep enough to be lakes. And the largest freshwater wetland is Pantanal, which is a seasonally flooded plain in the upper basin of the Paraguay River Basin. It covers 68,000 square miles and lies in a basin between the Andes mountain range and the Brazilian plateau. Alright, so let's get these mapped. So you're going to want to look at your tropic and humid subtropical climate regions, specifically all the tropical ones, CFA, CWA, CWB, and CWC. Identify any areas in your basin where rivers would gather and slow down in relatively low-lying plains. So these are just going to be areas where maybe they're moving quickly and then all of a sudden you have really long stretches of one elevation. And these could be large valleys mostly surrounded by higher elevation areas. And if they are large enough to put on a global map, mark these as freshwater marshes and or swamps. And then you'll want to look at your river deltas and any that are flowing over particularly flat coastal plains, so essentially anywhere where you have large stretches of that same elevation and you haven't indicated anywhere else that these would be particularly hilly. Where they join the ocean, you can have large saltwater marshes and swamps. So you can go ahead and add those in. So I sort of marked here on this map the areas that would really be relevant for these. And then this is what it looked like once I added them in. I don't have a lot of marshes and swamps, but over here where this plain is particularly flat, you can sort of see I have a number of marshes and swamps. Same thing down here. This is all relatively flat. I have one here where this would kind of slow down, and I think I have a delta here. So that's essentially our rivers and wetland biomes map. And now that we have these mapped, we're going to look at the rest of the global biomes, in addition to the wetland ones. And I really appreciate you watching. If you enjoyed this video, please give it a like and let me know your thoughts in the comments. And if you have any questions, found any problems, or have a request for something to add to a later video, please let me know. And yeah, I will see you in the next one.